going to be talking about Chapter 18 here, OpenStax College Physics. I'm Dr. James Wetzel, and I will be taking you on this journey. Let's go ahead and get started. So Chapter 18 is on electric charge and the electric field. We're going to start by talking about static electricity and charge and the conservation of charge. So there we're going to define what electric charge is. We're going to describe how the two types of charge interact. We're going to describe three common situations that generate static electricity and then state the law of conservation of charge. Then we'll talk about conductors versus insulators. We want to define what a conductor and an insulator are. We want to explain the difference. We want to give examples of each. For example, you have a cable that connects your computer to your computer to the wall, which carries power, but it doesn't shock you when you grab the cable. So there's a conductor inside and then an insulator on the outside. And then we'll talk about three methods for charging an object, and then explain what happens to an electric force as you move further from the source. And then define polarization. 18.3, we start to quantify things with Coulomb's law. We want to state what that law is. This is an equation, and we want to explain what it does and how you can calculate the force between two objects separated by a distance due to the electric force. And then we want to calculate that force between, let's say, an electron and a proton. And then compare that force, the force between two charged particles with mass, compare how the force, the electrostatic force compares to the force of gravity of attraction between them. Which one's stronger, for example? A particle like the electron has both mass and charge responds to electric forces, and mass responds to gravitational forces. So we want to compare the two. So we want to describe the force field, the electric field, and calculate the strength of an electric field caused by a point charge, how to do that. And then we want to calculate what the force is exerted on another charged particle by the electric field. And then explain the relationship between the electric force on a test charge and then the relationship to the electric field strength. Then we'll get to 18.5. We'll talk about electric field lines and what happens when you have more than one charge. We'll calculate the total force exerted on a charge if you have more than one charge, and then we'll describe an electric field diagram of a point positive charge or a point negative charge, or a negative point charge, a positive point charge. And what if it has twice the magnitude? How do we draw that? And then we'll draw the electric field lines between 2 points of the same charge, between 2 points of opposite charge. Okay. Then we talk about electric forces in biology. We'll describe how a water molecule is polar. We'll explain what electrostatic screening is by a water molecule within a living cell. I'll probably gloss over that pretty quickly. And then 18.7, we start talking about conductors and electric fields in static equilibrium. Static equilibrium just means you've got a conductor that can carry charge, but there's no charge moving around. How does it behave when it's just sitting there? How does it behave when you put it in an electric field? And all these things are going to be important as we continue. So we just want to learn these properties. We want to list the three properties of a conductor when it's in electrostatic equilibrium. We want to explain the effect of an electric field on free charges in a conductor. We want to explain why no electric field may exist inside a conductor. We want to describe the electric field around the Earth. We want to explain what happens to an electric field applied to an irregular conductor. We want to describe how a lightning rod works, and we want to explain how a metal car may protect passengers inside from the dangerous electric fields caused by a downed power line touching the car. Very interesting. You've always wondered that, haven't you? Whew, that was a lot. Okay, 18.8, we want to talk about applications of electrostatics. Or just talk about the Van de Graaff generator and some things like that. All right, let's get started. Whew, boy. Starts out with a picture of Ben Franklin with his kite. You've heard about this, but you probably have no idea what the heck's going on. So he's got a kite up here, and then he's got a conductor hooked to a key. So this thread that's out in space, out into the sky, is conducting. And what happens is when it's out there in space, there's a separation of charge. It ends up building up some excess charge on it. And then he's between the edge of the rope that's conducting and him, he's tied a little bit of a different string that doesn't conduct, so he's not going to get shocked. So he's holding that, and then the key is hooked to the conductor part. And then this gentleman down here, some say it's his son, puts his hand near the key, and then sparks start coming off the key. And this was just showing that somehow when they flew the kite up into space, charge was building up, and it wanted to come off, and it was jumping off in the form of sparks. And this is when Ben Franklin started to experiment with electrostatics. Um, so you have Ben Franklin doing experiments trying to determine the properties of static electricity. You had Luigi trying to do experiments and realize that if you shocked frog legs, they twitched. So there was some electrical nature to muscles. And then he found that if you put copper and zinc, just two different metals, together, you could create the same thing. So that would generate a current, basically. And then Alessandro Volta, who was inspired by Luigi, he developed the battery. And then by developing the battery, using this idea that if you can just create a potential difference and you get current to flow, that's an important thing. So we're trying to figure out what electricity is, and this is kind of the history of it. So there's forces we've talked about in the previous section 151 course, the earlier chapters of this textbook. Friction, the normal force, chemical forces, push forces, pull forces, tension in a rope. All these forces, when you touch something and you feel it, all of those forces ultimately are from electricity and magnetism, are from electric forces. So from chapter 18 on, we're learning more about the fundamental interactions that give us all these other forces that we deal with. The four fundamental forces you may remember: electromagnetic, that's the one we're going to be studying now. Gravity, that's what the first 17 chapters dealt with. Mechanics, things moving, gravity, orbits, forces from the normal force, that kind of stuff. That's gravity. But we have the strong and weak forces. Those are nuclear forces. Those forces take place, they're subatomic forces, so we don't really notice them. I mean, we notice their effects because we're alive and existing using those forces, but our senses aren't sensing those as much. So this chapter starts with charges and electrostatics, and then we're going to move on to charges that are moving, which is called a current, and then we're going to learn about magnetism, which is a result of moving charges. So let's get right into it. Section 18.1, we're starting to talk about the conservation of charge and static electricity. So you know static electricity, when you rub something, you might have done this when you were younger, or maybe still now with your roommates. If you shuffle your feet along the carpet and then you touch them, you'll shock them. In this case, this young lady, she rubbed this dog, and then what happened by doing that is you put a lot of charge onto the dog. So the dog now has a lot of charge on it, or you take a lot of charge off. In any case, it becomes net charge, either net positive or net negative. And what happens when you have like charges next to each other, they repel. Okay, they repel each other. There's a force pushing them apart. So all of the little dog's individual hairs all have the same charge, and they're all trying to get as far away from each other because there's a force pushing them apart. Okay, so this is the opposite case. You've got a cat with a balloon stuck to its head. It's stuck via magic. Okay, it's a magical force, electricity and magnetism. The static electricity is holding that balloon on the cat's head. Same thing here. In this case, the balloon and the cat are opposite charged. So rather than causing the hairs to spread apart, like in the first dog, this case they're opposite charged, so the balloon is stuck to the cat. All right, so what makes plastic wrap cling? What makes when you pull your clothes out of the dryer and you hear and then everything's stuck to it and it's really hard to unfold the shirt because it's all stuck together? That's static electricity, right? This effect obviously has been known to humans for a long time, running around shocking each other, like really lame wizards. They can just gotcha. I mean, it's kind of like wizards, but just you'd think if you wanted to be a wizard, you would want a little more than just that. But if you want to know what it's like to be a wizard, you can just do that. That's literally what wizards do. So we're wizards, I guess. We're just very lame, weak wizards. So you can determine the characteristics of static electricity by rubbing things together. You saw the lady rub the dog, and the dog could rub the lady, and vice versa, and you could determine what got charged with what. Or you could rub the cat and then rub the dog and see if the dog and the cat stuck together, or try to determine what the charges are, what are possible, what are out there. Sometimes you have to be careful about static electricity. For example, getting out of the car, you're going to build up a charge. You usually touch the side of your car and you get a little bit of a shock just to let that charge off so you don't blow up your fuel tank. In hospitals too, you wear little booties if you work with oxygen tanks, just to avoid the chance. It's rare, but you could, release a wizard shock and explode an oxygen tank. Or if you're trying to put circuit boards together and then you accidentally, we are wizards in that sense, but we don't have good control about when our wizard powers. So we just shock things and blow cars up, and circuit boards, we fry chips and so on. So you just have to be careful. You wear little special bands when you're working on circuits, so you don't discharge onto the circuit board. You can discharge off to somewhere else. Okay, so some characteristics of static electricity. Static electricity is explained by a physical quantity called electric charge. So we've talked about mass before, all these other properties. Electric charge is another property that particles, that objects have. There's only two types. That's nice. Plus and minus. There's no reason there's only two types. I mean, there's not like a rule that it had to be two types. It just is. The rule about the opposite charges attract, like charges repel. And we'll talk about the force and how to calculate how strongly they attract and repel in a little bit. But it depends on the charge, and it depends on how far apart the charges are. Those are the two values that you care about. So how do we know that there are only two types of charge? We rub things together. Cats and dogs, people and blankets and dogs, whatever. If you rub, for example, you take a glass rod and you rub some silk on it, the glass will become positively charged, the silk will become negatively charged. Now they will attract each other. So you can rip electrons off one thing, put it on another thing, and now you've got a positive and a negative charged thing, and they're going to want to be attracted to each other. Similarly, if you had two sets and you took them off this one, took them off that one, now you've got a positive rod and another positive rod and a negative cloth and another negative cloth. If you took the two cloths together, two negatively charged cloths together, they will repel each other. And if you take the opposite charged ones together, they'll attract each other. So this is trying to say, you had a string holding this rod so it can freely pivot around like that. You bring your negatively charged thing to it, it's going to be attracted to it. In this case, they're both positive, so it's going to be repelled away from it. In this case, they're both negative, so they're going to be repelled away from each other. That's what that figure is trying to show. So where do these charges come from? Can you create or destroy charge? Is there a smallest unit of charge? How does the force between charges depend on distance? These are the questions we're going to try and answer. The charges come from electrons and protons. So we're answering the two questions here. Where does charge come from? From charged particles like the electron or the proton. The smallest unit of charge is carried by one electron or one proton. You can't have less charge than that. So you can think of an atom, and that's what this picture is over here, as a positively charged nucleus surrounded by a cloud of negatively charged electrons. So the electrons are attracted to the nucleus, and one electron has this amount of charge. So this is your new number that you have to know and love and memorize, like Avogadro's number or something else. It is 1.602 or 1.6 times 10 to the minus 19 coulombs, okay? And that's called the fundamental charge, or sometimes you'll see it as QE, which is the charge on an electron. In this case, we've got two lines here to indicate the absolute value because an electron is negatively charged, so we're taking the absolute value of the electron just to have the magnitude, which is 1.6 times 10 to the negative 19 coulombs. So Coulomb is the unit, SI unit for charge, and it's how much charge something has is measured in coulombs. Okay, if you want to figure out how many electrons are in one coulomb, in other words, if you have one electron, it's this many coulombs, 1.6 times 10 to the minus 19. If you take 1 over that, then you can calculate how many protons or how many electrons you would need to get 1 coulomb of charge, and it turns out to be a bunch. So normally in real life we don't do a lot with just 1 or 2 electrons or protons, so we use the unit coulomb even though you need 1,000 quintillion protons in order to have 1 coulomb. We don't deal with 1 or 2 electrons at a time. We usually deal with capacitors that are hold a lot of charge. So that's why you might be wondering, why don't they have a different unit? And it's because most of the time we're dealing with a lot of electrons. Okay, so the electron appears to be fundamental. There's no substructure. This little diagram here is showing you that the proton is actually made of quarks, which are subatomic particles. They're smaller than a proton. So there's no such thing as a proton per se. A proton is just the effect of quarks hanging out together. So quarks carry fractions of a charge, but the net effect is they all add up to one QE, one charge on the electron. Okay, so you can separate charges by rubbing materials together. You can also move charge through a circuit, like powering a battery or using a battery to power your phone. But the key is whenever you do anything with charge, you can't create or destroy charge. You can only move it around from different places. That's the law of conservation of charge. So any theoretical or mathematical framework, any of the financing and accounting for electricity and magnetism will have to keep track of where the electrons are at all times. Okay, you can't just disappear an electron and reappear an electron somewhere. Okay, the charge has to be conserved. 18.2, conductors and insulators. Okay, and here they're talking about E equals mc squared, and you can take energy and make matter and make energy, but even in that case, you're conserving charge. Charges, the net charge is 0 on both sides of this equation, I guess, because from out of pure energy, you always have an electron and an anti-electron produced whenever you have matter created out of energy. It's always created in matter-antimatter pairs. This is actually an interesting point because there's a really big open question right now. If you've studied, nerdy things like the current topics physics people are trying to answer, one of those questions is, why is matter everywhere? Why isn't there antimatter? Why is our universe mostly matter? As far as we can tell, matter and antimatter are the exact same things. Matter just has positive charge and antimatter just has the opposite charge. Okay, so what's going on there? We don't know the answer, but in our experiments, every time we produce particles from pure energy, it's always created in equal amounts of matter and antimatter to preserve that charge conservation. So we're not exactly sure, but we think nature prefers matter over antimatter on a very small amount. Open question. Anyway, keep an eye out for that. Section 18.2, conductors and insulators. Substances like salt water and metal allow charges to move through them easily. The electrons in these substances are not bound to individual atoms. That's the key. That's what makes it a conductor. These substances are called conductors. Now the thing is, a conductor in this chapter doesn't necessarily have to be actually conducting electricity. It doesn't have to be hooked to a battery to have conductor properties. It doesn't have to be plugged into the wall to have conductor properties. So when we talk about conductors and insulators, we're talking about a metal that the electrons can move about, or a plastic that electrons can't move about. Okay, so keep that in mind, that when we talk about conductors, we're not necessarily going to hook it up to a battery yet. We'll do that in later chapters, but for now we're just talking about the concept that electrons can move around on them, whereas on insulators like glass, you can't do that. So you can charge substances in two ways: by contact, so you can rub things together, or by induction. We're going to talk about the two ways here really quick. Charging by contact, you can take this is an electroscope, you can take a charged rod, bring it close to this electroscope. Basically what it's going to do, when you make contact, the electrons are going to jump off of it, and then when you remove the rod, now there's a net positive charge on your electroscope, and you can use this tool to measure charge. So that's charging by contact, and you can also by rubbing things together, the same idea. Induction is a little bit trickier thing. You can transfer charge with some more wizardry. In this case, you have a conductor. Now this is why we talk about conductors. In this case, this is what a conductor is when it's sitting still. The positive charges don't want to be next to other positive charges. So you're never going to find all the positive charges hanging out at one spot and all the negative charges hanging out at another spot. They're never going to separate themselves, because as soon as you get positive charges pushed to one side, they're all going to spread back out to get away from each other. So every one of these electrons are like, everyone's just stay away from me as much as possible. So everyone's equidistant from each other, everything's spread out, nothing's happening. But when you bring your magic wand that's positively charged to the conductors, in this case we have two metal spheres in contact, when we bring this positively charged rod to the conductors, what is going to happen? Think about it. What is going to happen if I bring this positively charged rod over near this conductor? What do we know? Opposites attract and like repel. So these electrons are going to be attracted over. They're going to feel a force, a magic force, and the electrons are going to all move over to be near this positive rod. I like to think about it as these are fans of this celebrity. These are not fans, they're disinterested, so they're going over here. It says like the parents at a Justin Bieber concert, okay, with their kids or something. All right, so this is how you can, so we've induced what this is called a polarization. We've induced a polarization where everybody's positive over here and everyone's negative over here. And then this is the trick. Before taking away our wizard wand, we separate them, break the bridge. Now we take away the rod. There's no way, even though the force stopped, the magic wand is gone that was attracting the people here, the electrons over here. We broke the bridge, and now this has a net negative charge, and now this has a net positive charge. So you're, okay, this is weird. You're like, what are you talking about? Okay, this is weird. I get it. But this is just to understand that charges can move around, that you can manipulate them, and this is what we're learning about, is how to manipulate charges because we all want to be wizards on some level. All right, the other way to do it is you can take your sphere, bring your wand near it, and then there's your polarization again. You separate the charges out because there's an external force that is allowing you to do that. If that was not there, everything would be mixed. Then what you do is you ground it. So this is another term you're going to learn, grounding the sphere. If you ground the sphere, that means you just hook it to some place that can either take charge or put charge onto your source. So something, another sphere was what we did in the previous problem, but it could be literally the ground. Literally dig a hole and put your wire in the ground. So that's why they call it that. But it's a reference point, basically. So you hook it to ground, and that's the symbol for it. What this does is it allows electrons to flow onto this thing because it's going to steal electrons from there. It's feeling this force. It's going to pull everything up. And then, so this is A, B, C, D. So you bring the rod near it. You induce the polarization. You ground it to allow more electrons to jump on it. Then you break the ground. Now the ground is gone, but there's an extra amount of negative charge. Then you take away the rod, and now you're left with a negatively charged sphere. So this is just another technique to charge stuff up, okay? So again, I know it's weird, but you're learning about it. All right, so 18.3, Coulomb's law. This is where it gets mathematical. This is Coulomb's law. It's easy. The force between two charged particles, it literally is how many coulombs times how many coulombs and how far apart they are. That's the whole equation. This equation looks a lot like G m1 m2 over r squared, doesn't it? Where g is k and m is q. So in this case, we've replaced the Newton's gravitational constant g with some new constant, let's call it k. We've replaced charge with mass, but distance is still meters, okay? So this is really interesting. This k value is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Okay, Newton meter squared per Coulomb squared. So that's what k is. Let me erase k there and say Newtons meters squared per Coulomb squared. So you see you have Coulomb times Coulomb, so that's Coulomb squared. You have meter squared on the bottom, meter squared, and k is what gives you the newtons at the end of the day. So this is our conversion factor to make sure we get newtons at the end of the equation for this law. Okay, so what is it? What are the problems you're going to have to solve? I'm going to give you one charge and another charge. I'm going to say they have this many coulombs and this many coulombs, and I'm going to say they're a centimeter apart or a nanometer apart or some meters apart. I'm going to ask what's the force on them. And you're going to know, well, if they're both negative charges, they're going to push away from each other. So the force is going to have this magnitude. Notice the absolute value sign. We don't care whether it's plus or minus yet. And then you know, after you do the calculation, you look and you say, oh, they're the same charge, so that means they're going to push each other apart. Okay? So the question is 18.1. If we go back and write gm1m2 over r squared. Okay, so this is if you have an electron and a proton. Okay, the electron has mass, the proton has mass. So that would be M1 and M2, and we could put them far apart. But there's also the fundamental charge on both these things, and the question is which force is stronger. So we can solve both equations to figure out which one's stronger, and they do that here in this example. So they say compare the electrostatic force between an electron and a proton separated by this far. Compare it with the gravitational force for the same thing. Okay, so first we do Coulomb's law. We know that K is 8.99 times 10 to the 9. We know that each electron and proton have the same charge, 1.6 times 10 to the minus 19, and we know that they are that many meters apart from each other. And we get that the force between them, 8.19 times 10 to the minus 8 newtons. So if you had an electron and a proton next to each other, this is the force that they would feel. You could set that force equal to ma and solve for the acceleration of the electron and the proton if you wanted to. Okay, but this problem is asking for us to solve Newton's gravitational equation to figure out what's the force of gravity between them. So we do the same thing. We've got g, Newton's constant. We've got the mass of the electron and the mass of the proton, same distance between them squared. Look at this. Compare that, and that. Okay? 8 times 10 to the minus 8 newtons for the electrostatic force, and 3 times 10 to the minus 47 newtons for the gravitational force. So if you divide those two numbers, you get that the electrostatic force is times 10 to the 39 times more powerful than gravitational force. That's a nonsensical number, 10 to the 39. You have no idea how much that is. That's a bunch. That's a whole bunch, okay? So this is what makes it hard to study black holes and everything else, because every time we try to create in experiments anything at that level, all these other forces, the weak force, the strong force, the electromagnetic force, they're so much more powerful than gravity. We can't tell what happens to a proton and electron from the gravitational interaction when they're that close together, because these other forces just overwhelm everything. Okay, so that's Coulomb's law. Those are the types of problems you're going to have to calculate. You have two charges, how far apart, what's the force on them? What if you have three charges? How are you going to do that? You've got a charge here, a charge here, and a charge here. Well, what you do is you ignore this charge, and then just do these two. And then ignore that charge, and then do these ones, okay? So it's not, and you just keep doing it until you're done. All right, oops, I skipped ahead. Section 18.4 is about the electric field. All right, so fundamentally, when you hit a baseball with a baseball bat, you hear sound and it feels like a contact force. But fundamentally, at the smallest scale, what's actually happening is Coulomb's law, is you're getting an electric repulsion, and they don't want to be close to each other. So when I'm doing this, my electrons they're just fighting back. Okay, so it's an electrostatic force ultimately. You can think of then, how does this happen? You can think of a charge like an electron. How does the proton know the electron is here? They're far apart from each other. What's going on? You can imagine a charge as having an odor that the other charges can smell or sense. Like charges are repelled by the odor, opposite charges are attracted to it. We need a source charge to create an electric field, and we need a second charge to detect the field. All right, so this is a little bit tricky, but follow me here. The force between two charges is K Q1 Q2 over R squared. What if we only have one charge? What if we only have one charge? Okay, if we only have one charge, let's just get rid of it. It's not there anymore. So this here is what we call the electric field of a charge. It's the first part of Coulomb's law. And then we can, if we want to calculate the force on another charge, we bring it in and just multiply it to our equation. But when we get rid of that second charge, this becomes the electric field. And you see what I did there? I just added a little e there. Now we have the electric field. Okay, so that's it. The only way for a charge to sense another charge is to imagine they're connected by a field. The important thing is that we consider the field a real thing. It's not an imaginary construct that we think we need just to make things work. We do believe it's a real thing. So the electric field is just defined as the Coulomb's law, the force between two charges, and divide by one of the charges. So then you just have one charge and you just have the electric field. So this is a little bit, I like the way I explained it just now a little bit better than this definition, because when you cancel out that second charge by dividing, you just get that kq1 over r squared. Your q2 is not there, you don't care about it. You just imagine that a single charge by itself creates a field that has this strength, which is just determined by its own charge. Okay? The electric field only depends on its charge and then how far away you are from it at any point. All right. The let's see here. So then these two examples here are just having you calculate the electric field of a point charge. So it's asking you to calculate the strength and direction of the electric field due to a point charge that has 2 nanocoulombs. 2 nanocoulombs is 2 times 10 to the minus 9. Okay, and then you're 5 millimeters away from it. So to determine the electric field, all you have to do is kq over r squared. K is the same, 8.99. It's 2 nanocoulombs. You are 5.5 millimeters away, or 5 millimeters away, whatever they said, squared. Yeah, 5 millimeters away, squared, and that's it. It's 7.19 times 10 to the 5th newtons per coulomb. So if I brought in another charge, multiply that, if I multiply this by another coulomb, that's supposed to be a coulomb, then you'll have newtons left over, and that's how you get the force back between two charges. But that's it. That's how you calculate the electric field. Now, it wants you to calculate the strength and direction of the electric field due to a point charge. So you got a point charge here, and then it says 5 millimeters away. So this distance is 5 millimeters, and it wants to know the direction and magnitude. So we just calculated the magnitude, 7.19. The direction is going to be pointing along that the same direction you calculated the radius r in. So whatever direction you calculate r along, that's the direction of the electric field. It's always pointed in that direction. Okay, it's a vector. So electric field is a vector. You got to pay attention to its magnitude and direction. Section 18.3 wants you to calculate the force exerted on another point charge. You bring it into the same problem. So all you have to do then is multiply that electric field you just calculated. All you have to do is multiply it by this charge. So they say we bring in a charge of 0.250 microcoulombs, and you put it 5 millimeters away. What's the force exerted on it? It's literally that 7 times 10 to the 5th that we just calculated times that charge, and you get this force, 0.180 newtons. Okay, so that's it. That's all you have to do, and that's how you can calculate an electric field, the force between two charges, or the electric field. Okay, so field lines. Field lines are how we communicate electric field strength as a function of distance and direction and the vector nature of electric field lines, or electric fields themselves. So the electric field is a vector. This means it has magnitude and direction, and so we need electric field lines to demonstrate and show off what our field looks like. So electric field lines begin and end on charges. They can never cross each other. I'm going to go over these rules in a little bit here. But basically, if you've got a positive charge like this, there's two ways to draw it. In this case, you can see the difference is there's 3 arrows here versus 1 arrow. What's the difference? This is showing you that at this point, right at the center, this arrow is in that direction but that long. At this point, the arrow is in the same direction but shorter. At this point, same direction but shorter. So what that's telling you is that as you move away from this charge, the electric field is getting weaker because the arrows are getting shorter, which means the magnitude is getting less. Whereas over here, all they're communicating is the direction of the electric field. Okay, so these are just two ways to describe what the electric field looks like and how strong it is and how it's behaving as a function of distance. The key is your electric field is kq over r squared. Okay, oops, oh geez, kq over r squared. That's a 2. Oh my gosh, 2. Okay, so that means if I go a distance r away from that charge, the electric field there is going to have a certain strength. If I go a distance r anywhere else, same strength. If I go a distance r this way, because it's symmetric, anything on this radius where r is constant, the value of the electric field is going to be the same. Okay, so that's an important fact to keep in mind. So you care about not just the magnitude but the direction of the electric field, but when it's a nice point chargey type setup like this, it's symmetric and uniform all the way around. These electric field lines, they go off to infinity where they eventually fade away and die. But the other important fact is that we think of positive charges. So if you look closely at that, it's a positive charge. We call them sources. And if it's a negative charge, we call it sinks. Okay, so sources, that means the electric field lines point away from a positive charge. The positive charge is the source of the electric field. And then the negative charge is the sink. So the arrows go into a negative charge. So that's just a common thing that you can easily be tested or quizzed on, is draw the electric field of a point charge. If it's positive, the lines better be coming away from it. If it's negative, the lines better be going towards it. Now, this is also a negative charge, so you're saying, okay, what's the difference between these two? They're both negative charges. Well, what if this charge is less than that charge? How do you communicate that? How do you tell someone looking at your picture which one has more charge? Well, the geniuses a long time ago struggled very strongly with this idea of how to do this, and they realized, let's just draw more lines if the source is stronger. So if this negative charge here is bigger than the other negative charge, then you can demonstrate that by drawing multiple lines or more lines. So that's all that's talking about. Okay, so electric fields for multiple charges just add together. Let's say you take one charge and another charge, and you want to know what the total electric field is at some point due to both of them. You can just add them together. But it's not so easy because electric fields are vector quantities. So you can't just add vectors together like normal numbers, like scalars. You have to consider their directions, right? So this means we need to add electric fields together vectorially when we have multiple charges. So in this section here, there's a confusing picture. They should have drawn multiple pictures, but it's one picture with a lot going on. What they're asking you to do in this problem, okay, let's look at the problem. It says, find the magnitude and direction of the total electric field due to 2 point charges, Q1 and Q2, and then calculate it at the origin of the coordinate system as shown in this picture. So what that means is there's a charge Q1 here, a charge Q2 there, and they want to know what's the total electric field at the origin center here. Okay, so what do you know? You know that if you have one charge, it's going to generate an electric field. You have another charge, it's going to generate an electric field. You know that the electric field that it generates is going to be going outward like this. So both of these charges are going to be generating their own electric fields like that. So that means this charge down here, the electric field is going to be pointed up at that point, even though it's going off in every direction. It's going to be pointed up there. And we know the electric field from this one, even though it's pointing everywhere, is going to be pointing that way at the origin. So right here at the origin, you're going to have an electric field pointing that way and an electric field pointing that way. Okay, and then so we need to calculate what that electric field is for both of them and then add it together. So let's simplify this picture. This is the problem we have. We have Q1 down here and Q2 over here. So how do we do this? Well, let's imagine this charge has its own electric field just going off in every direction, and that means going along this direction. At the origin, the electric field is pointed that way. So we can calculate what E is here, the magnitude. It's KQ over R squared. What is R? It's this distance here. And what is K? It's a constant. What is Q? They tell us in the problem. Okay, we can just calculate what the value of E1 is at that point. And the direction is going to be off that way. And then we can do the same thing right there and then have the electric field lines going up at that point and calculate what the electric field is here using that R, and then calculate the total contribution at that point. So if we want to know the electric field at the origin, we can just ignore all the other electric field lines and just look at what's happening at the origin. Okay, and so that's where it is. So all we have to do is calculate the electric field there from E1 and from E2, and then just add them together vectorially. So once we do that, there we go, head to tail method. and then our net result is going to be, so that's E1 and that's E2, and that's going to be the X component of the net and the Y component of the net contribution. Okay, so if that's E1 and that's E2, how do we figure out the total electric field? The total electric field is the length of that vector, which is the square root of E1 squared plus E2 squared, and this is E total. And you can just calculate what that is. So that's what this problem is showing you, what it's trying to explain how to do. You've got Q1, let's see, there you go, Q1, Q2. So first thing you do is calculate E1 and E2, and then next thing you do is you add them together to get E total vectorially. So if we go through this, the first thing they have you do is calculate what E1 is, and that's just K, Q, and then how far it is from the origin, KQ1 squared. And then E2 is just KQ2 over R squared. So you have E1, you have E2, and then you want to get E total, and then you just add them in quadrature, as we say, and then that is going to give you the net, the total electric field contributions from both of those. To find the direction, if we go back to here, we've got E1 and E2 here. Well, we want to find the direction. We can say that it's a certain amount of degrees up, and that's the opposite over the adjacent. So the tangent of this angle is the opposite over adjacent. So that means the angle itself is the inverse tangent of E1 over E2. Okay, so that's the fun stuff. So that's, of the types of problems you're going to have to solve, that's of the harder flavor. Okay. All right. So moving on then to electric fields. What happens if you have more than one charge? Not only do the electric fields look a little complicated, but they get a little bit messy too. So in this case, we have two negative charges and a positive and a negative charge, and this is what the electric field lines look. So there's a couple rules here that the electric field lines can never cross. They begin on positive charges, end on negative charges. So that means two negative charges, if you bring them close to each other, there's going to be no electric field in there, and they're going to repel each other. In this case, the source and the sink are connected, and so this is just what the electric field looks like around positive and negative charges. So you just kind of have to be aware of this. This is called, or these are called dipoles, and these are a common thing in electricity and magnetism. So just be aware of that. So there's some rules. Field lines, they must begin and end on positive charges, or at infinity in the hypothetical case of isolated charges. The number of field lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. The strength of the field is proportional to the closeness of the field lines. The more you draw, the stronger the field is. And then field lines can never cross. That's an important thing. And then the direction of the electric field is tangent to the field at any point in space. What does that mean? What does it mean to be tangent to the field at any point? This drawing is a horrifying attempt at trying to explain that. Okay, so what it means is, what does it mean to be tangent to a line? Like at this point, what would tangent to that line be? It would be off in that direction. Okay, my marker's quite too big. Okay, so that's tangent, 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 right? So it's turning as it follows that line, but it's tangent to that point, which means it's just glancing across it. So the electric field at any point is tangent to those field lines, and that's what they're trying to tell you. Okay. Electric forces in biology, I'm going to kind of ignore this. You can read it, but it's just telling you that electrostatic forces are really powerful in part of life, and it's the reason DNA is the way it is, and so on. And then water is it's a H2O, so you can just read about that. It's pretty interesting. Section 18.7, conductors and electric fields in static equilibrium. So conductors contain free charges that move easily. When excess charge is placed on a conductor, or a conductor is placed into an electric field, the charges respond and they reach static equilibrium. And the question is, what does it look like when this happens? If you put a conductor in an electric field, it becomes polarized. It's like inducing the charge, like we did with the spheres. So this is an electric field, an external electric field, and then you can see that the charge on the conductor is separated, so it's induced a charge, so the conductor becomes polarized. If you have a conductor with extra charge on it, the extra charge, if you have a net charged conductor, like a sphere of metal that's charged, all of the charge resides on the surface. That's one fact about it. And there's no electric field, no net electric field on the inside of it. So inside of a conductor, the electric field is always zero. Just outside of the conductor, the electric field lines are always perpendicular to the surface. That's again what this is showing you too. They're always perpendicular to the surface, always perpendicular to the surface. So at any point, there's a 90-degree angle as it leaves the charge on a surface. And then any excess charge resides on the surface. How do you generate a nice uniform electric field? This is an object called a parallel plate capacitor. And you have a series of positive charges, a line of them, and then a line of negative charges. So they cannot cross each other, these lines. So they have to begin on a positive charge and end on a negative charge, and this is how they behave. And then near the edge of the capacitor, it kind of leaks out. We call it fringe effects. They're just bulging at the edge. Okay, and then the rest of chapter 18.7 talks about lightning and what happens when you have an irregularly shaped charged object. The electric field lines always come off perpendicular to the surface, so it looks a little weird, but it behaves just like you'd expect. This is a lightning rod. You can read about that, and the general idea is to help dissipate, cause lightning to strike that instead of something else. And then 18.8, applications of electrostatics. So we have a, let's see, eraser. Okay, we have a Van de Graaff generator here. You've probably used one. They're these silver balls, and then you put your hands on them, and then someone turns it on, and then your hair starts to stand up, and you can shock people with it. All that is a mechanical rubbing machine, and it's just depositing charges on this conductor as it rubs. Okay, then there's laser printers, so the laser will charge the paper, and then the ink will be attracted to just those parts. And then there's some other things here that you can read about for applications. But then we get to the end of the chapter. Okay, so that's the main stuff. So we're gonna have, as far as the review, what you care about. There's charges, plus and minus. There's a fundamental charge. The electron and the proton have it. Charge is always conserved. There are two types of objects, conductors and insulators. Coulomb's law is the way you can calculate the force between two charged objects. What is the field that's emanating from a charge that when you bring another charge to it, it can sense it? We call that the electric field. And it's the hypothetical force between two charges, and you divide one of the charges out just to get what your electric field is set up by the charges. And then field lines, it's the way to draw the electric field so someone can understand what it looks like around your charge. Then we talk about 18.6, 18.7, 18.8 are more general information stuff. The thing about 18.7, what you care about is that a conductor can be polarized by an electric field, static equilibrium. There's no electric field on the inside of the conductor, and so on. Okay, so now what I want to do is talk about the homework. I might have to log in again. There we go. And there we go. Da 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 da. Okay, and we're just going to go through these really quick. So if two uncharged objects are rubbed together, one of them requires a negative charge, then the other one is going to have to acquire the opposite charge, right? A balloon can be charged by rubbing it with the sleeve of your sweater while holding it in your hand. You can conclude from this that the balloon is what? Okay, so think about this. If you charge a balloon up by rubbing it and you keep your hands in contact with it while you're rubbing it, is it a conductor or an insulator? Because a conductor would allow the electrons to travel. So it has to be an insulator, right? Because if it was, I mean, what are balloons made out of? Rubber, right? What are wires, cable, insulation made out of? Rubber, right? So it must be an insulator. But if you were to rub it and temporarily take some charge, but it was a conductor, it would just take the charge back, right? It would just go back and forth. So the balloon it must be a insulator. Okay, so you venture out on a cold winter morning to warm up your vehicle. You have layers of cotton polyester blend clothes on, and from walking on carpeting, you have accumulated a positive charge. Your car is considered a neutral conductor. As you place your hand near the door handle without touching it, what happens to the charges of your car? Okay, so this is just like bringing the rod to the sphere. It's going to induce a charge onto the handle. They're going to polarize, push some of the charges away from the handle. Some of them are going to be pulled towards it. So if you accumulate positive charge, the door handle is going to become negatively charged because the negative charges are going to be attracted to it. A positively charged rod is brought near one end of an uncharged metal bar. The metal end furthest from the charge from the rod will be what? So you bring a positive charge near here. The negative charges are going to fly over here, which means the opposite side should be positive as well. Okay. Oh, and then there's a little twice as much as the end nearest the rod. Okay. Law of conservation of charge. If you took some charge from here, you're not going to have twice as much charge over there. It has to be the same amount. We've got two scenarios, two charges, two spheres. Okay, this one you have to think about. You've got a plus charge and a minus charge, and they're hanging like this, and then you let them go. What happens after you let them go? What is the final state? So they want you to sort these. Do the spheres come to rest in contact, or do they come to rest separated? In other words, after they touch each other, do they neutralize each other, or do they stay charged so they're going to stay apart from each other? So you've got a plus Q and a minus Q, and gold is insulators, so that means they won't transfer charge to each other. So if I bring the plus Q and the minus Q, they're going to come together and they're going to stick together and they're going to be attracted to each other, and that's going to be it. What happens if you bring this minus Q to the plus Q, but it's a conductor, so it's bigger and it's going to conduct some charge, but what is it going to do if it's minus Q more, if it has more minus Q than the other one? Is it going to push charge onto the insulator, or is the insulator going to take charge from it, or what's going to happen, right? And then you've got these two, equal amounts of minus Q and plus Q, again insulators, so they'll stick together. The conductors, minus Q and plus Q, when they get together, what are they going to do? And then same thing. So just think about each of those and what would happen. And remember, an insulator cannot conduct charge, but a conductor can conduct charge. So after they come in contact, what's going to happen? Are they going to stay separated? Are they going to transfer charge to each other, and then therefore neutralize whatever force they had? Okay, metal sphere A has a charge of minus Q, and identical metal sphere B has a charge of 2Q. The magnitude of the electric force on sphere B due to sphere A is F, some amount F. The magnitude of the electric force on sphere A due to B must be, okay, so you got two spheres. They've got some amount of charge, minus Q and plus Q, and they're saying the amount of force on B due to A is F. What about A due to B? Okay, what is the reverse thing? Well, you don't even have to do anything because you know Newton's third law, which says for every action there's an equal and opposite reaction. So if the force on B due to A is F, then the force on A due to B is also F. It has to be. And the force on them is Q times 2Q over R squared. It doesn't matter whether it's A or B. So the answer is F. All right. Consider the arrangement of charges shown in the figure. 4 charges of equal magnitude Q but varying sign are placed at the corners as indicated. A positive charge Q is placed at the center. What is the direction of the force, if any, on the center charge? Okay, so let's look at this picture. You've got plus and minus and minus and plus. All right, let me do a little screenshot here. And the first thing is asking, what is the charge? What is the force on the charge at the center? So the charge Q, I believe, I have to take a look at this. Charge Q, little q, is positive as well. Okay, so the Q at the center is positive. All right, so if the charge at the center is positive, then this charge is going to push on that charge. This charge at the top right is going to pull on it. This charge on the bottom right is going to push that way, and this charge on the bottom left is going to pull that way. So those four vectors are all equally balanced. So there's going to be no net charge, no net force on that center charge, right? Because this is balanced perfectly by that one, and this one is balanced perfectly by that one. Okay, so there's going to be no net charge at the center. Okay, so that first net force, there's going to be no net force on the center charge. Okay, because of that. But now it says suppose that the charge Q were to be displaced slightly. So if we go back to that, and we're going to have a force there, a force there, a force there, a force here, then the question is, what happens if we put this little q there instead? What's going to happen? Where is the net force going to be now? Because it's not going to be right at the center, it's not going to be balanced. So where is this net force going to be? So at that point, you're going to have, okay, we're going to have our q here, and then so this charge is going to push down like this. This charge is going to pull down like that. This charge on the top right is going to pull that way. This charge down here is going to push that way. Okay, but we're going to have it's unbalanced. So you're going to have a net force that's going to push this thing in some direction. And what I want you to do is figure that out. But that's how you do that, is draw arrows, draw your vectors. You can draw them a little more neatly than I did, to figure out which components cancel out and which components don't cancel out, and therefore which direction is this thing going to move. Okay. Now you got these diagrams. Place what you got. So you remember that sources and sinks. The picture on the far left, the arrows are going into it, so it's got to be a minus charge. In this case, they could either be both minus or both plus, but again, those arrows are emanating from the charges, so they have to be both positive charges. And then in this case, again, are they emanating? Which one are they emanating from, and which one are they going to? Which is the source and which is the sink? Okay, which diagram correctly indicates the direction of the electric field produced at each point by the positive charge? Okay, so this is a little bit tricky because it's just these weird pictures, but the question is, which diagram indicates the direction of the electric field produced at each point? All right, so we have a positive charge. Now, what do we know about the electric field? We know that the electric field is always pointing away radially from the charge. Okay, so we just have to find the picture where the electric field is not pointed like that, but pointed like that, just pointed away at that point. Whatever point, it has to be pointed away from the green circle. Whatever point you pick, the electric field is always going to be pointed away radially from the electric field. So remember, at every point in space, there is an electric field, and that electric field has a value, kq over r squared, where r is the distance you are from the charge. All right. So we got another thing in the figure. 4-point charges lie on the corners of a square, with a 5th point charge located at the center. The 2 leftmost charges, negative charge. The 2 rightmost have a positive charge. What is the direction of the total force on the charge at the center? So let's do this again, screenshot. So we've got our charge at the center, which is, I think they said it was positive. Oh man, I always forget. The center charge Q is negative. Okay, so the center charge is negative. So we're going to have our negative charge here, and top left is negative and negative. So that means they have the same. So the force due to this one is going to push that charge away. The force due to this one is going to push that one away. This is a positive one. So the force on this negative charge is going to pull it towards and pull it towards. So now you've got the y components of both of these forces cancel out. So you got y component, y component, y component, y component, but the x components all add up. So you're going to have a net force pushing this thing straight to the right. Okay, so that's how you do that. And then what is the direction of the electric field at the center of the square due to the four charges? Yeah, it's to the right. I think that's just what I did. Okay, delete this. Next. The picture shows a rod made of silicone, a swatch of leather, and an aluminum ball initially uncharged. So what happens here? Okay, so you know, when you, there we go. Actually, I think this is negative. So when you rub the, come on. Let's see if I can do this. No. There we go. Come on. Here we go. Okay, the swatch becomes positively charged. The rod becomes negatively charged. So the rod over here is going to be negative charged as well. And when you do that, there we go. When you do that, then the metal ball is going to be induced as well to be opposite. Okay, a certain lightning bolt moves 50 coulombs of charge. How many QE is this? So you divide that by 1.602 times 10 to the minus 19 coulombs. Get the total number of charges. An electron and a proton, they're separated by this distance, about the distance of a single atom. What's the magnitude of the electric interaction between them? So this is just kq over r squared. What's the magnitude of gravitational interaction? So this is mg m1 m2 over r squared. And then it'll be 10 to the 39 times stronger or something like that. So you'll divide those two numbers together and get the electric force to be stronger. Okay, as a skeptical student, you want to test Coulomb's law. For this purpose, you set up a measurement with a proton and electron are situated 959 nanometers from each other, and you study the forces that the particles exert on each other. As expected, the predictions of Coulomb's law are well confirmed. You find that the forces are, so you should know what that is. You also find the magnitude of the force, and you can calculate the magnitude of each force. So you can just do that. There we go. What is the force on the charge located at 16 centimeters in the figure, given that Q1 is this? The other two charges are located at these positions. So this is, the question is, what is the force on that charge due to the other two charge? Okay, so this is easy. This one you don't have to worry about vectors. You can just say you want to find kq over r squared, where q is either that q or this q. And then you add them up at that point. Okay, sorry, not just q, but times 2q then. So the Coulomb's force is going to be, object eraser, yeah. The Coulomb's force, kq1, q2 over r squared, for both of these. So in the first case, I'm going to ignore that charge, and I'm going to say F on the first one and the second one is going to be equal to kq times 2q over r, 2, 4, 6, 8, 10, 0.1 meters squared, so 10 centimeters squared, and then ignore this one, and then calculate F 3, 2 is going to be equal to k q times 2q over, and then we've got 2, 4, 6, 0.06 meters squared. And then we just add those two together because this is a plus and a minus charge, and that's a plus and a minus charge, so they both have the same, they're going to add up. Sorry, they're not, because this one's plus and this one's minus, so this is what you have to be careful about. This force from this charge is going to be attracting it this way, but this one's going to be attracting it that way. Okay, so which one's stronger, which one's weaker, so you'll subtract those two values to get the net force on that charge. Okay, but it's as simple as just doing Coulomb's law twice and then adding them up or subtracting them. Okay, so two particles, one with this charge and the other with that charge, are this far apart. What is the magnitude of the force that exerts on each other? So that's just kq1, q2 over r squared, so you calculate that. But now the two new particles with identical positive charge, q3, are placed the same distance apart, and the force is measured to be the same as the original particles. What is q? Okay, so what you're going to do in the first case, you're going to say, oh, the force is K Q2 over R squared, and you're going to calculate the magnitude of the force there. Now we're going to replace those two charges with Q3, so we're going to have KQ3 squared, because they're two of the same, divided by the same R squared, and that has to equal this F. So then you're just going to solve for what Q3 is. All right, next. Uranium and iron atom reside a distance 57.1 nanometers apart. The uranium atom is singly ionized. The iron atom is doubly ionized. Calculate the distance r from uranium necessary for an electron to reside in equilibrium. Ignore this gravitational attraction. Okay, so this problem sounds scary and hard because they added the word ionized. All that means is this is plus 1 QE and this is plus 2 QE. So we're going to have, this is the same problem we just did, and you're going to say that the force of uranium on the electron is equal to K Q E over R, little r squared, because we're a little r apart, and we have plus Q and the positive charge and the minus charge, but they both have the same charge. Okay, we need this to be in equilibrium, so we need this force to equal the other force, K. That's going to be the charge on the electron, but then it's going to be 2 times charge on the electron because there's two fundamental charges there, divided by big R squared. Okay, and we know what big R is, so we know what big R is, we know what Q is, it's just the charge on the electron. We know everything, the only thing we don't know is little r squared, so you're going to solve for that, and then that's going to give you the answer. Then consider this figure. Using the symmetry of the arrangement, determine the direction of the force on the charge. Can I get this smaller or bigger or what? Shoot. Okay. Yeah, and then calculate them. Okay, so this is your hard one. A, B, C, D. Okay, so A, B, C, D. You got A, B, C, D. All right, so you're going to do the same thing. A, B are positive, so this is positive, positive. C, D, negative, negative. Your center charge is positive, okay? So you're going to get a push force there, a push force there, a pull force there, a pull force there. So the net force is going to be down, okay? All you have to do is figure out this is your R. We know that the sides, they tell us what the sides are, so you're going to have a length here like that. Then you're going to figure out how long that is, okay, which is going to be half your length, and you can, L and L here, and you can figure out the square root of the length of that. So that's going to be your distance, R. You can calculate each electric force. Then you're going to know that the X components cancel each other out, okay? So all you're going to do is add up the Y components of all these things. Now this triangle is a 45, 45, 90 triangle. So you might have to use tangents or cosines or sines to figure out your components. And if you need more explanation on that, come and see me on how to do that. Or if you'd like to see that one worked out fully, let me know. But this is taking a long time, so I want to keep going. I think that might be okay. So then you got an electron on the x-axis. Find the magnitude direction of the electric field at this distance. And so that's just a straightforward problem to calculate the electric field. Now this is another tricky one, but not that tricky. So we've got a ball that's going to be charged. It's hanging from a ceiling. So it's got a mass. So there's only a couple forces on this thing. You've got gravity pulling down, and you've got the tension in the rope, and then you've got the electric field pushing over. So that means the X component of the tension in the rope is equal to the electric field strength. They're balancing each other out. And then the tension in the Y direction is equal to the weight of this thing, mg. Okay, so the tension, you can calculate what that is. It's the X component is going to be, maybe like T cosine theta, and then the Y component is going to be T sine theta. So you know the mass, you know the G, you know the angle, it tells you what that is. So you can solve for the tension. Then you take that tension, plug it back into the equation up there. You already know what the angle is. Boom, you've got the electric field strength, and you're done. Okay, delete. And next, I think we already did that one. And I think this is too many questions, so I'm going to remove that one. And these two charges are located in the xy plane. Okay, so this is the problem I did in the book where we've got two charges and they are located in the xy plane, and you want to calculate the electric field, the combination of the electric field. So you've got x equals 0 and y equals, so you've got a particle here. Second charge is x equals 1.5 and y, so you got another charge located there. Calculate the x and y components of the electric field, and then add them up. So that's your job, okay, at the origin. Okay, so all you have to do is figure out the electric field at that point, and then you're going to have some net electric field pointing with some components in the different directions. So once you figure out E1 and E2, those are going to be your, you just break them up into the components. Okay, that's everything. I think we did a good job. Now you'll know everything about electrostatics. All right, see you guys later. Bye.